Okay. Good. Just a second, I'm gonna share my presentation. Okay.
I think you can share your presentation now, Prof.
Yeah, okay. Now I think it is. Okay. Share. Can you see it?
Yes, it's clear. Please, please.
Okay,
Yeah,
can you see the
yeah,
full
it's clear.
screen?
Yeah, we
Yes?
see it.
Okay,
Yes.
perfect. Okay. I would like to thank Dr. Zidan for this beautiful introduction. I'm very pleased and honored to be here today with you and present to all of you some of my little knowledge in this field. First of all, I apologize for being a little bit weak. I had a surgery a week ago and I'm still recovering, but I didn't want to change the date of the presentation because I was committed to do it on time. So please excuse me if you don't find me that very fit. Thank you all for being here. Today we will talk about quantum manipulation of coupled qubits using an off-resonance radiation field. As actually I was advised by Professor Shaban Khalil that there is a wide spectrum of audience in this talk, and he actually advised me to do a good introduction and a good background of the field of quantum computing and qubits, coupled qubits, and actually this is what I'm planning to do today. So I'm gonna try hard to make you enjoy the talk. We will talk about the background. I will try to take you into a kind of a journey through the quantum computing field in one perspective. It has so many perspectives actually, and I hope that you guys will enjoy it and find it informative. Okay, so we will talk about basically classical bit versus quantum bit, which is the qubit. What's the difference? What are the promising what are the promising qubit candidates? Why the Heisenberg interaction is important when we talk about qubit interaction. Also, we will talk about symmetric qubit systems and asymmetric qubit systems. And we will conclude as we go through the different parts. Can you all hear me well? Am I clear to everyone?
Yeah, yeah.
Okay,
We
thank you.
hear you.
Yes, very nice.
Very good. So basically, we will talk about research in the very general map. Research in quantum computing now, you can split it into two big pieces, theoretical and experimental. And the theoretical part is more about algorithms and software developments, plus studying the system evolution, studying the decoherence problem, loss of entanglements, entanglement sudden death, which present the main obstacles in realizing a real practical computer. On the other hand, the experimental part, which I don't work on actually, is about how to manufacture qubits in the lab, how to prepare a good system that can be used to store information and process it. Before proceeding, and as I said, I think there are many people who are not aware probably what is a classical bit and a quantum bit. we probably, all of us are very aware of a classical bit, which is the unit where we store information in a classical computer. So basically, classical computers store energies as either 0 or 1. And the classical bit basically does that using a transistor. And the transistor has a current passing through it. Basically, if there is a current passing through the transistor, we consider that as 1. And if we consider no current basically passing, we consider that as a 0. So this is how we deal sort of of how the classical bit works in a classical computer. So all the time you have either on or off, 1 or 0. This is of course a simplified, very simplified model, but just telling us that we have 1 or 0. That's all what we have. When we talk about a quantum bit, a qubit, how do we make a qubit? That's the good question. And basically, okay, okay. So basically, any two-state quantum system can be used as a qubit in principle. Of course, there are restrictions and requirements, but in principle, a quantum bit is nothing but a two-state quantum system. And this means basically you can think of it as an atom that has only a ground state and an excited state. So 2 levels. And the thing is, if you put your system in the ground state, like if you have an electron, for instance, and that electron is living in the ground state, then you talk about basically a 0. So it's like I'm storing 0 on this quantum system. If I, on the other hand, adding or exciting the electron to go to the higher level, which is the first excited state, I'm going to call that basically 1, and I'm storing now 1 as the information. But what is so special about quantum mechanics is that you can basically store a linear combination of the 2 states. So you can have your electron living actually between 0 and 1. And roughly speaking, we can say that I have a combination of 0 and 1 now. So my electron actually can be living between the 2 states. And it's really living between the 2 states, as we know from quantum mechanics. So it's not completely in 0, not completely in 1. It's in a linear combination of the 2. Of course, we have to, if we do, formal work, we have to add linear coefficients. But for now, just think about having your electron living between 0 and 1. So that's the main idea. Okay, so that's what gives the quantum bit or the quantum mechanics the huge power that we are trying to utilize in quantum computing. Because think of the following. What if we have, okay, so what if we basically, okay, I'm gonna use the laser pointer here. So the question is, what if we have 2 classical bits? Okay, what happens is you will have 0, 0. Okay, so the left one is 0, the other one is 0 or 0, 1 or 1, 0 or 1, 1. So the 2 classical bits can choose between those 4 different choices. Okay, and for a classical computer, it has to pick only 1 choice out of 4. Okay, why? Because basically classical bits can live in 0 or 1 only. So if the left one is in 0, then it's in 0. The right one is 0, so 0. So the only choice is 0, 0. Now also 0, 1, 1, 0, and 1, 1 are other choices. But at the end of the day, you have to pick only 1 choice out of all those 4 choices. While if you look at the quantum bits, if you have 2 qubits, you can have actually a combination of all possible combinations of the zeros and ones. You can have 0, 0, 0, 1, 1, 0, 1, 1, all in one state. And this means I'm carrying all this information in one piece. And basically, this means now, while for 2 bits, as you can see here, you have 2 classical bits. You have to choose 1 out of 4. Here, you can carry the 4 pieces of information together at the same time. You make 2 to the power n different states in one piece, and you carry it with you. That's the so much power that this quantum computing is providing us. So here you have only 2. So basically 2 to the power 2 is 4. So you are carrying 4, states in one state when you combine them together. Imagine that you have 10 qubits. If you have 10 qubits, you talk about 2 to the power 10, which is going to give you 1,000. So you have 1,000 pieces of information, all possible permutations carried in one state. That's huge thing. Now, can we really do quantum computing? Excuse me. Can we do really qubits out of any 2-state system? Can we just take any system and do a qubit with it and make it a qubit? Actually, the answer is, of course, no. You have very high restrictions. You have to define it very well. You have to be able to control it. You have to combine, the 2 qubits together with a quantum entanglement. So they have to have a quantum correlation between them so we can do this linear combination of them. So actually, it's more complicated than just saying a qubit is a 2-state system. Now, probably we should go to the next and talk. Here is a very simple comparison between classical and quantum qubits bits. And this is 0 and 1, but here it's a superposition of 0 and 1, or you can have 0 or 1 or a superposition, combination of them. Measurements does not change the classical bit, of course, but measurements change the qubit because it's a quantum system. Deterministic results here, but here it's undeterministic results. As we know, we can make a copy of a bit, but we cannot make a copy of a qubit, which adds a higher layer of security. One number of a string bit, here you store several numbers of bits simultaneously. So those are all very big advantages. Okay. The qubits that are very good candidates now for quantum computing are divided into 2, categories, natural and artificial. Natural are natural atomic and molecular systems, like atoms, ions, molecules, under certain conditions, of course. And here artificial are superconducting qubits and quantum dots. So we have actually 2 different types. Of course, the artificials are more than that, but simply we can focus on superconducting qubits and quantum dots. So those are the type of qubits that are very good candidates for quantum computing, these days. Okay. The question that anyone may ask, why do you need artificial? Why don't we just use natural? Actually, it's a very good question. We will talk more about that. So the very famous qubit systems that interact with each other are here. I'm going to talk about them actually in more details in a moment. But before proceeding, I want to so those are again the newly engineered quantum systems, semiconductor quantum dots, superconducting circuits. Here, the natural atomic systems that have been customized are ultra-cold atoms, trapped ions in electromagnetic fields, Rydberg atoms. I'm going to talk more about that in a moment. Why we like artificial atoms? Why they have some kind of advantage over natural atoms? in some sense, because actually we can manipulate them easily. They are made by our hands in our labs. You can build, so those looks, if you look here, this looks like a quantum well. And as you can see here, if you apply an external field to this, system, it stays with two states, with two levels, and it doesn't really shrink them, and you can control them here and here in quantum dots and superconducting qubits. While in natural atoms, if you apply an external field, it's going to disturb the energy levels enormously. And that's why we like artificial atoms, because they provide for us atoms that add demand with energy gaps that we design, and we can control them very easily. So that's why. One of the big steps forward in the field of quantum computing was done with these two guys who won the Nobel Prize in Physics in 2012. Basically, if you look there, those two guys did extremely important step forward. I'm talking here about Haruchi and Wineland. And basically, when the Nobel Committee gave them the Nobel Prize, when they were awarded the Nobel Prize, the reason is for groundbreaking experimental methods that enable measuring and manipulating of individual quantum systems. Those guys were terribly clever in their labs. If you look at the first one, who was Haruchi, he was basically sending individual Rydberg atoms through a cavity. And the cavity basically is there, and basically the Rydberg atom can cross the cavity from one side to the other side, and it can tell us about the photons, the single photons states inside this cavity. So this guy was able to control a single Rydberg atom and to observe it and monitor it when it comes out and read the information on it. So that was terribly good and different, okay? And so it's like you are playing with single atoms and photons as well. Here was the work of Wineland. And Wineland basically was able to capture ions using laser, which is electromagnetic radiation. So he captured them and was able to manipulate them, store, to change their basically states. So if it's in the ground state, he can basically put them in their ground states, and he can excite them to the excited states using the laser beams. And he used electrodes to confine them in the middle, where those electrodes are creating electromagnetic fields themselves. So he had, again, the ability to manipulate single atomic systems and basically control them and tell us if they are in this ground state or excited state. That's amazing. And if you think about it, this is really very interesting. And this is exactly, if you remember what we said at the beginning, you need to define a qubit, but any two-state system can be defined as a qubit. But the thing is, can you control it? Can you put it in 0? Can you put it in 1? Can you put it in a linear combination? So those guys actually made a big breakthrough when they did that, by basically being able to play with the Rydberg atoms and to play with the trapped beryllium ions inside an electromagnetic trap. So this is, again, the trapped ions in electromagnetic fields that we were talking about. And here you can manipulate them and store information on them and use them for quantum information processing. So that's really interesting. One of the other systems, of course, if you look at this system here, those are natural ions. So this is not an artificial atom. But those guys were so clever to the extent that they were able to manipulate them and control them and their states. Here, this is another type of promising candidates for quantum computing, which are trapped atoms in what's called optical potential traps. And they create those traps, optical traps, by using intersecting laser beams. So they make a minimum in the potential energy, and they can hold atoms inside those trapped potentials, and they can manipulate them. Okay, so this is again is another good candidate, and you can have thousands of them inside this lattice. Okay, this is another candidate, a good candidate for quantum computing, which is quantum dots. If you create two quantum dots, which is here, this is a quantum dot. So this is a two-dimensional electron gas, and you have many electrodes here. That's usually created in a heterostructure of semiconductor material. You end up with two-dimensional electron gas in this layer here, and you put electrodes, and those electrodes can confine the electrons into, you know, a very small circle, and basically, which is in almost zero dimension, and that acts as an artificial atom. So this is an artificial atom now, and you can control the energy states, and you can play with them as you wish. And you can make those act as a spin-spin interaction with each other, and you can use it as a qubit, actually. So those can be used as two qubits interacting with each other. Very good. Also, this is another kind of electron spin interaction where we use the electron spin as a qubit in nitrogen vacancy in diamond. And this is another very good candidate for quantum computing. One of the things that I wanted to mention is that actually we also have what's called the superconducting qubit. And the superconducting qubit is another type of qubits that can be used. And there are so many different types of superconducting qubits. And they actually act as a qubit. But the good news is that the people who are working in the superconductivity field, they basically used what's called a resonator, coplanar resonator, okay, which is made of a superconducting circuit that can create a microwave radiation. And you can use this radiation to interact with different types of qubits. For instance, if you have trapped atoms like here, or a quantum dot, or impurity spin like the diamond that we showed a moment ago, or electrostatically quantum dots. So all those guys can be basically used on a superconducting resonator where they enjoy or experience an electromagnetic radiation created by that resonator. So every one of those needs lectures of talking and, and discussions about their properties. But one interesting thing is that people started to say, why don't we actually combine artificial atoms like quantum dots or superconducting qubits with natural atoms and make what's called a hybrid system? Why? Artificial atom, you bring an artificial atom with a natural atom. Why? Because each one of them has good properties and advantages and disadvantages. So one of them, which are the natural atoms, they have a very long lifetime, but they have a very bad processing ability. While artificial atoms like quantum dots and superconducting qubits are basically very good in processing, but they have very short lifetime. So what people proposed is basically, let's combine them. And actually, many experiments have realized that to combine natural atoms with artificial atoms to create basically what we call it a hybrid system. So a hybrid system is made of it, and that's the thing. Okay, very good. The thing is, you can have, of course, as I said, you can have superconducting circuits with atoms and spins and waveguide as a source of radiation that connects them. And there are so many applications of that. This is a qubit, superconducting qubits, charge qubit, flux qubit, phase qubit. There are different types of qubits that you can make from superconducting circuits. And you have, in the other hand, coplanar resonator, which produces a microwave radiation field to interact and control those guys. This is again a hybrid circuit, as I said, where you have a superconducting flux qubit with NV centers. Okay, and you can put them here and you can use the radiation field to play with them. This is all very important for our problem that we are studying, because basically we are so interested in basically in studying qubit systems interacting with the radiation field. So that's why this is so important. I wanted just to emphasize that here. Okay, so what do we do here? Basically, okay. This is again many different forms of hybrid systems. Okay. Okay. One of the very important questions, why do we care so much when we study quantum computing systems about the Heisenberg spin-half system? Remember, I told you that a quantum bit, which is the qubit, can be modeled as a two-state system. So in many cases, when people study the quantum systems, basically the qubits, they basically represent them as a spin system, a spin half system, which has, for instance, its downward direction as the ground state, upward as the excited state. So it's like down 0, up 1, or the other way around. But they basically model the qubit as a spin half system, a spin half, a spinner, basically. And so that's why people paid a lot of attention into the Heisenberg spin half system to describe the interaction that happens between qubits. Because if you have two spins, the interaction between them is basically Heisenberg interaction, XYZ interaction. And so we can use the Heisenberg system to model the interaction between the different qubits. And that's basically why we paid a lot of attention to them. This is giving different types of systems that are basically good candidates for quantum computing, and they can be described using the famous Heisenberg Hamiltonian or the XYZ Hamiltonian. And basically in every case, there are studies which shows what are the correct J's that you have to use, how they look like, what are the range of their energies, blah, blah, blah. So, and that was taken from this very interesting paper here. It's a pioneering paper. Good. So the Heisenberg spin model is simply you have two spins, and each one of them has three components, as you know. And basically, you consider XX interaction, YY interaction, ZZ interaction between the different components of the Heisenberg model, those two spins, I mean, the different components, the interaction between the different components of this two spins. And basically, okay, so we have Jx, Jy, Jz as the interaction strengths in the X, Y, Z direction, respectively. So when we come to a chain, for instance, if you have a chain, like one-dimensional chain of spin have particles with periodic boundary conditions or open boundary conditions, you basically have, okay, a spin that is interacting with its nearest neighbors with a J interaction. And we can describe that with the XY model or XYZ model. And we can have a time varying magnetic field that acts on the system. For instance, we studied that in one of our projects. And also we studied the case when J itself is changing also with time. So what happens if you control the exchange interaction between the spins? So we did that in different works before. And this is how so because we have limited time, I'm gonna just show you what this is. So actually, this is the XX. So this is the Hamiltonian of the Heisenberg XYZ spin model. And this is basically, the XX interaction, the YY interaction, okay, and the ZZ interaction. So there are three terms, one for the X direction interaction. We are representing, remember, you can represent S in terms of the Pauli matrices. So S is sigma over 2 if you take the Heisenberg constant as 1. So basically, this term here represents the XX interaction. YY interaction is here, ZZ interaction is here. And finally, we have an external magnetic field H, which could be a constant or a time varying magnetic field, depending on the problem you are studying. We actually studied H time dependent and G time dependent in different works, as I mentioned, and it was published a long time ago. Now, the thing is, this is the very important Heisenberg XYZ spin model. And as you can see, it talks about N of the spins. So if you go back here, sorry, I have to jump back. We have N spins, simply. And so this is the model for N spins. Now, the thing is, by controlling what's called gamma, which is here and here, and delta, you can actually change the strengths of the interaction, the relative strengths in the X direction, Y direction, and Z direction. And that makes a huge difference, because by taking gamma and delta at different values, you can study what's called the Ising system, or the XX system, or the XY system. So you will have three different systems basically to study here. Okay, now this system we talked about, the Heisenberg system, especially in the dimensional case, it has what's called quantum phase transitions. And there are classical phase transition and quantum phase transition, but I'm going to skip that because it needs a lot of explanation. If anyone is interested, can communicate with me and we can talk about it. Okay. Now, basically, as I said, we are so interested in studying a qubit with another qubit and couple them to each other and control that coupling with each other and make it coherent. Because if they lose the coherence interaction between them, they are dead. We don't have any quantum computation. We cannot store information or process it. So one of the very, very famous models to study atom field interaction is the Jaynes-Cummings model, of course, and we all probably have heard about it or we know it. Okay, and basically, if you look at what this is, you have basically an atom inside something that looks like a box, which has an electromagnetic radiation confined inside that box. And the radiation here is interacting with this two-state system. If you think about this, it looks like Jaynes-Cummings, they thought about a qubit interacting with a radiation field like, you know, I don't know, probably 80 years ago, if we do our calculations. And they came out with their very famous model, which talks about what's the interaction between a two-state system and a radiation field. And we all know that this Hamiltonian is made of three pieces. It's made of the Hamiltonian of the field, the Hamiltonian of the atom, and the interaction between the field and the atom. And this is how it looks like. So this is the field term, this is the atom term, and here is the interaction between the field and the atom. Okay, so this is how the Jaynes-Cummings model was. And as I said, it's very much like as if you have a two-state system, which in our ideas, it's a qubit, interacting with a radiation field, which is very crucial for quantum computing. Because as you saw, many of the systems that we are considering, we are treating them using radiation fields. Good. So here, basically, omega is the frequency of the radiation field. Omega node is the frequency of the single. This is the omega here is the frequency of the radiation field. Omega node here is the energy gap of your two-state system. Okay, and G is the coupling strings between the two guys. Okay, perfect. Of course, A, dagger, and A are the field operators, while sigma, plus and minus, and sigma Z are the Pauli spin matrices that we all know. Okay, now, as you saw here, we were talking about a single qubit with a radiation field, which looks so much like a very simplified model. And the next model was the Davis-Cummings model. And basically in that model, more atoms were added inside this cavity, inside this box. It's not only one atom anymore, but one or two or even more atoms where you can add n of them. So now, if you look here, we have two atoms. And if you look here, we have n of them, okay? Now, so this is really was a good, a good generalization and a step forward in the Jaynes-Cummings model. Okay, what happened after that is that we can write now a Hamiltonian. So if you put n equals 1 here and here, you end up having the old Jaynes-Cummings model. But if you look at what we have here now, this is a model where we have n atoms inside the cavity, and they all are considered as two qubits, the two-state systems, which means you have a chain of qubits. Very good. What was really in the original Davis-Cummings model is that there is no interaction between the atoms inside your cavity. The atoms here do not see each other. Each one of them can see the field and interact with the common field of all of them, but they don't actually see each other. And that was a big thing. And the reason behind this is that the coupling between the atoms, the natural, simple, regular atoms, the coupling is very, very small. So this is why When people came with those models at the early times, they thought that there's no reason why should we really put extra efforts to look at the coupling between the atoms. Well, think about these two atoms inside a cavity. So again, you have two qubits. Each one of them is a two-state, as you can see, two-state, where the energy gap is h bar omega node and h bar omega node, and the radiation field that's interacting with the qubits, it has a photon energy h bar omega node. So actually, this is what people call it a resonance case. The radiation field and the energy gap of the atoms are basically identical. So two identical atoms with two levels each, and each atom is coupled at resonance, delta equals 0, to the same radiation field with coupling strengths lambda 1. So they are exposed to the same radiation field with the same coupling strengths lambda 1. So this is interacting with lambda 1 and this is interacting with lambda 1. But the important thing is people started to say, oh, let's add here between them, let's add an interaction. Why? Why people started to think about interaction between the two qubits? Oh, because we are now having artificial qubits, which, like artificial atoms, which came out to have a strong interaction between them. That's why. Even the manipulated atoms, like the Rydberg atoms, because they are so large and they have a very strong dipole-dipole interaction. If you put two big Rydberg atoms inside a cavity, they will couple to each other. So that's why people started to say, oh, we have to take lambda 2. So now we have lambda 2 as basically the coupling between the two atoms. And this is the thing. So basically, we have now two qubits interacting with each other with a coupling strength lambda 2. They are symmetric. So you have two identical qubits. And they interact with the same radiation field with the same strengths of coupling with the radiation field. Okay. Now, this problem was solved already, and it was in the literature. And here comes our first project that we did a few years ago. We decided to think about what would happen if we are out of resonance. Having a resonance between the energy gap of the two qubits and the radiation field energy makes the mathematical problem very easy. Not easy, but relatively easy. But if you take into account that the frequency of the energy gap of look here, the energy gap of your atom compared with the photon energy is different, where you are out of resonance, that makes the problem much harder. And we worked on that. So that was one of the projects we did a few years ago. And we studied the case when omega minus omega naught is not 0. Of course, we can reproduce the old results when delta is 0. And we did that too. So we studied the general case of delta not 0 and also the case when delta is not 0. And in that case, what happens basically is, okay, in that case, what happens basically is the following, that your Hamiltonian now has two frequencies. It has omega and omega node, and not like before. And when you go through the calculation, that makes the problem much harder to solve. And we worked on that Hamiltonian, and we went through some terrible calculations, but were doable at the end. And we provided an exact analytic solution for the problem. And we studied the problem in the interaction picture. and we were able at the end of the day to provide basically the wave function of the system, okay, at any, so we started here. I don't want to take you to the technicalities of the calculations because I don't want really you to get lost, but I can tell you basically that this is our Hamiltonian, and here is our initial state, and we considered an initial state that is a linear combination of all possible states of the two qubits. Here, for instance, this is excited state for qubit 1, excited state for qubit 2, excited state for 1, ground for 2, ground 1, E2, ground 1, and ground 2, a linear combination of that, and it's multiplied by a coherent state representing our radiation field. So this is my initial state, and we studied the time evolution of the system. This is, of course, the coherent state of the radiation field, and this is Qn, which is here. And I think some of you are familiar with those things already. And basically, we worked in the interaction picture, and we calculated the interaction potential. And we were working on basically this as the wave function at any time t. So when we solve this equation, we should get this, which can be obtained if you get A, N, and B, and C, and D. Those coefficients were the targets. So we were able, after some calculations, to get them. And we got them in a final form. I'm not showing all the calculations, of course, here, but I'm showing some of the results. And basically, after some considerations of all the possible complex roots, we were able to find out a solution. As I said, once you know A, N, B, N plus 1, C, N plus D, N plus 2, you got the exact solution. And those are some of the parameters inside those solutions. So you can imagine how was terrible. And my student at King Saud University, actually, this project, I did it in collaboration with Professor Sibawayh. But unfortunately, Allah yarhamu, he died 2 years before we were able to publish this paper. So he started with us the project, we worked together, but then he died. And at that time, I was at King Saud University, and my master student, Wiamsh, who was an extremely good student, worked on the mass. She completed all the calculations, and we were able to finish the project successfully at the end. One of the things that we were studying in that project is what's called finite time disentanglement, which is what the people call it now, entanglement sudden death. And entanglement sudden death, you can understand it from this graph. Entanglement sudden death happens in a very short period of time. It's here. You just see that the entanglement is vanishing. Entanglement is the quantum correlation between the qubits. As I explained before, what differentiate a qubit system from a classical bit system is the quantum correlation, which is represented through entanglement, quantum entanglement. And the quantum correlation between a 2-qubit system or two atoms, let's say, if it happens in a very short period of time, people call that, and actually that was by in that paper by okay, so that was first introduced in this pioneering work by you and Eberly in 2004. And they later explained that in more detailed in their Science Review article in 2009. And basically, as I said, you may talk about sudden death of entanglement. Here, as you can see, basically, it means the entanglement is dying very rapidly in a very short period of time. That is in contrary with the usual vanishing process for entanglement or correlation, which goes asymptotically over a long time. Why sudden death is very bad? Why sudden death of entanglement between quantum systems is very bad? Because it doesn't give you the chance to resist it or to prepare the system to take a counter, like a counter action. So basically, if the death happens for someone in a very short period of time, you may not be able to save him or her. And that's exactly the same with quantum systems. If the entanglement between the quantum systems, the quantum correlation vanishes very rapidly, basically you don't have time to solve that problem. So you lose control. While for the other case here, you have time. So people can work on so many protocols and many processes to overcome the decay process that takes place here. So in our actually work, which we solve it here, okay? Basically, we talked about entanglement. Okay, this was a literature status. So people, many papers, this is a Journal of Physics B paper, came to discuss that. And this is another paper, talks about qubit spin path system and the interaction between qubits. Here is two-atom Davis-Cumming model, where they also studied entanglement sharing. There were sudden deaths of entanglement, of course, of Eberle and Yu. And many papers came out to discuss two interacting atoms in a cavity. That was a very important paper by Arturis, okay? And that was in Journal of Physics A. And nonlinear Jaynes-Cumming model for two interacting two-level atoms. Many papers came out to deal with this two qubits. In our case, we studied the entanglement and the population inversion between these two qubits. And as I said again, we have two qubits, and we have out of resonance radiation field with them. And we studied the time evolution and the entanglement between them. And we studied the entanglement sudden death as well. And we tried to see what values of the parameters of the system may take you to the region where there is a sudden death, and where are the parameter values that may take you out of that region, which is, of course, was a very important thing. This is two atoms, like Rydberg atoms in a cavity. And this is like two artificial atoms inside superconducting resonators. So those two can be an experimental realization of our theoretical work that we did in that work. We studied time evolution. We showed many things. I'm not going, probably I don't have time to go over all of this. You guys can look at the paper. But we studied basically things like what happens when you have sudden death and then revival of entanglement, for instance, how that is connected with the population inversion. And there we found that there is a very strong synchronization. We showed that actually, so there are so many results here, and each one of them needs a very long time to explain actually. But we presented some important conclusion for this symmetric system where we have two identical qubits. And basically, as I said, we presented an exact analytic solution for this complicated system, which is out of resonance with the radiation field. This was a breakthrough at that time. It's a very important system for quantum information processing. We showed how the entanglement sudden death, okay, can be controlled by tuning atom-atom coupling and non-zero detuning. And even more efficiently when we combine them. If you can combine non-zero detuning, which means off resonance, and atom-atom coupling, you can have a better effective we showed the synchronization between population inversion and entanglement dynamics. We did many things there. And okay. And that appeared actually in Optics Express in 2019. And me, my student, and Professor Sibawayh appeared on that paper at that time. And it was, I think, a very good paper. Later, we published another paper in Entropy about asymptotic entanglement sudden death in two atoms. It was the same problem, but we looked at the asymptotic behavior and the Ising interaction effect on the system. This is a model that recently we are studying. And I'm gonna very brief here. I think I probably running out of time. I'm sorry for that. So basically here, we are studying not two identical atoms, but two different atoms. In this case here, life becomes much, much more complicated because now there's interaction between the two qubits. And why are we doing that? Because there is hybrid systems where you can have qubits of different types inside the same cavity or same superconducting resonator. So basically, you can have a coupling between this qubit and the radiation field, different from the coupling of this guy with the radiation field. And we have different basically energy gaps. We have omega-1 and omega-2. And we studied this system recently. We are working on it. And basically, I have a master's student here in Sharjah University, Omar Kosaisea, who is working on that system. And we were able, after long struggle with the mass, to provide a good analytical solution, a good results. And basically, our analytical results were so complicated that we basically decided to check them also numerically. So we use MATLAB and Fortran and and Mathematica and other tools to double check, and we solved the same system basically numerically to compare with the analytical results, and they were complete agreement. We had some big amount of, as I said, results, a big number of parameters, because as you see here, if you look at the problem, you can see that we have lambda-1 and lambda-2 for interactions. Interaction between the two qubits is lambda-3. Each qubit is interacting with a different lambda with the radiation field. We have different delta I, which corresponds here to the frequency of each one of them. So it was really a much more complicated problem. Hasn't been solved exactly and completely for any initial state like what we did here. And we got some good results. Probably I'm not having time now. I'm running out of time. So we did some, as I said, numerical accuracy versus our analytic solutions. We studied different types of initial states, entangled and disentangled. And we studied early stage dynamics of the system. And we saw how the asymmetry, which means how much the difference between two atoms inside the cavity is going to make a difference in the time evolution of the system. That was our main target here, is to show how this asymmetry is going to make a difference. Breaking the symmetry that was in the original system is going to make a difference in the time evolution. And we got some nice results. I hope that I can go over them, but I'm already over 1 hour now. So anyway, so the asymmetry case give us very, very nice results too about how to maximize we studied what's called the Posido equilibrium state of the system, and we showed how we can maximize the entanglement after a long time, such that the system can live in under certain, of course, tunability of the different parameters. How can you put the system in a good entangled state, depending on the initial state, of course. Actually, we wrote a first draft of the paper already, and we are still working on polishing it, improving it. I hope that's going to happen soon. Our group, this is a very last slide, I promise. Our group is working on actually strongly interacting many body quantum systems. We study open quantum systems and critical phenomenon. I have a few students working on that. Other students are working on ergodicity breakdown and quantum teleportation. We work on interaction with radiation fields, like what we are doing here now, entanglement dynamics and the coherence effects when the system is interacting, your qubit system is interacting with dephasing or dissipative environments. Any students who think that they are interested in any of this, they can communicate with me or with us, and they can join us if they are really interested. Even if they work remotely, that's okay. And we may be able to invite them for short visits, actually, if we can. But in any case, if you are interested, please talk to us. Thank you all for your patience. I hope that was informative and good talk and good time for all of you. Appreciate your being here.
Thank you, Professor Jihad, for this interesting seminar about how can we implement quantum computing physically. If anyone has a question, please write down your question in the chat. Okay, Minna ask how can we join? Already we have a WhatsApp group. You can join. Please, Dr. Sarah, write the link of WhatsApp group here.
Yeah, I think if you go to the group,
Okay,
you can find, yeah.
Prof. Hisham Al-Ish, I would like to interact with Prof. Jihad through microphone for a minute. Is it possible? Yes, but it is possible. Please open your microphone, Prof. Hisham.
Assalamu alaikum. Thank you, Zidan. Thank you, Jihad. Excellent presentation as always. I am your colleague, and I'm pleased of the way that you are presenting. And I hope for your good recovery. And then it's very nice that what you have presented. I have a small question. And the idea is you have used the coherent state for the field as initial states. So I suppose that is the way that you think is because experimentally, usually we pump with laser, we have coherent state. But suppose we have different state, modified, deformed, coherent state, Fox state and so on. I think the result will be dependent also from the state of the cavity, right?
Yeah, actually, Fox state can be a special a case of what we did. People used to study those systems with simple Fox states to simplify the calculations. I think the coherent state is more general. But if you look at other different, as you mentioned, other different radiation field states, we didn't consider them yet, but we may look at them if you think that one of them is going to be very interesting and may change the results. But as I said, Fox states is, we looked at the other groups that did Fox state before, and we were able to produce the results easily from our results.
Yeah,
thank you, Professor Hisham. Thank you so much.
The state. Another thing I want to tell, if someone want to join us for master degree, to do master degree at Sharjah University, because I was teaching me on Dr. Jihad, Professor Jihad at the university. You are welcome, and we have a very high GPI. We can have a scholarship for that. So just as information.
I wanted to say that actually Professor Hisham and me and other two professors are members of a quantum computing and quantum information research group at Sharjah University. And so Professor Hisham is a colleague of mine and a very dear friend. And in this group, we have a good number of students who are working with us now. And as I said, if any one of you guys want to join us, just communicate with me or with Professor Hisham. And if you have a good GPA, you may get a scholarship to join, our group. It's not our condition. It's actually the university condition to have a good GPA so you can join. If you don't, they won't let us give you a scholarship or to join the group. Thank you, Professor Hisham. Yeah.
Thank you, Professor Hisham. Thank you, Professor Hisham. Any question? Thank you, Professor Jihad, for this interesting talk. And wait us for more seminars next weeks, inshallah. Thank you.
Inshallah. I wanted just again to say, if any one of you guys want to communicate with me, I'll be very happy. Anyone want to collaborate from the colleagues, we will be very happy to collaborate with. You can contact me through my email at University of Sharjah in UAE. You can get my contact information from Dr. Zidan. He himself is a very dear and good friend of us and a good colleague too. So you are very welcome to ask and communicate with us. Thank you guys very much.
Thank you, Professor. Assalamu alaikum. Please, Dr. Jahad, please close the meeting. Dr. Jahad, please close the meeting.